Thank you very much. First of all, thank you again to the organizers to organize this fantastic meeting. I've really enjoyed all the talks, and thank you for inviting me here. So what I'll discuss today is obviously not work that I've done all by myself. So first of all, I acknowledge the people who've been involved, and first of all, the late Bruno Eckhart, and most of what I'll talk today I've done in collaboration with him when I was a postdoc in Marburg before I moved to Edinburgh. And then there's Guido Boffetta, and a student who's worked with us in Marburg, and Christina Marchetti. It become obvious why Christina has been involved. Okay. So what I'll talk today about is really the transition to condensate formation really in 2D systems. But first of all, I'd just like to point out, I mean, as we know that quasi-2D flows occur at macro scale in the atmosphere. I should have removed this slide. Alex showed it already. I've just left it here as a reminder. So at sufficient height, so what you see here, as Alex explained, is the third-order structure function measured at different height in two tropical cyclones. And if you go to sufficient height, you see that you have indeed an upscale energy transfer. But what I really want to discuss here is the motivation that led us to look into non-universal transitions just in 2D turbulence, and that is unsteady dynamics in bacterial suspensions. So what you see here is the velocity field of a dilute suspension of Bacillus subtilis, and this is a very thin layer, and you're looking at it from below. And what you see is that this has a characteristic size of vortex. You can see here vortices forming a size of about 100 microns. And if you look for the size of the corresponding bacterium, that's about 5 microns. So this is indicated, I think only the people in the first few rows may be able to see it. You can see this size here. So you have in the system vortices much larger than the characteristic size of swimmers. Now, I'm not discussing this as a condensate here at all. In fact, if you now do something, okay. If you would, so this is a movie from an experiment. The reference is given here, and again, you might not be able to appreciate it from further back, but you actually see that there's a characteristic scale here. So again, there's a characteristic scale. So this type of what's often called bacterial turbulence is not the type of turbulence that we are mostly discussing here, in the sense that this has a characteristic scale that comes about due to the collective motion of the microswimmer, but we do not have turbulent cascades in this system. If you consider the spectrum, it has a peak, and it doesn't have the characteristic power laws that we would expect. And what we asked ourselves was, well, imagine just theoretically I could have microswimmers that would just swim much faster. So they would effectively force my system much stronger. Can I transition from this sort of spatio-temporally chaotic system, where I still have a single length scale, into what we know as a classical 2D turbulence system, in the sense that do we have an inverse cascade that eventually results in condensate formation? And what's the type of transition that we would expect? Oh, not that we would expect, that we would observe in this system. So that was the motivation, really, to look into whether we get a transition in PDE models of this type of system. So what I discuss in the next remaining 46 minutes, or 40 minutes and then plus questions, is a PDE model of this type of physics. So I'll talk to you about a short derivation of how to go into, how to get a PDE model for this, and then discuss the phenomenology of the transition, and then at the end I'll compare with 2D turbulence just by random forces. So that's when the non-universality comes in, because we see a different type of transition. Okay. So what we have essentially is, in 3D we know there's a direct cascade, in 2D there's an inverse cascade, and we're asking ourselves, broadly speaking, what's the nature of the transition to condensate formation, or the onset of inverse energy transfer? And this relates very much to what we've heard earlier today, and also Alex's talk on Monday. And just to emphasize, I'm not looking into 2D versus 3D dynamics. This is purely 2D. So there are no 3D fluctuations in the system. This is plain 2D. Okay. So to abstract it a little bit, in a way, our question is, if we take the 2D Navier-Stokes equations in presence of forcing and a large-scale friction, so that's in the bacterial setting, could be a friction with a substrate, then how does the condensate formation depends on the forcing? So in the active matter case, we will discuss active stresses that lead to small-scale linear, small local in scale linear instabilities, and we'll compare at the end with the standard random Gaussian distributed forcing, and we look into the effect of large-scale friction. So in principle, the control parameter is always the correlation between the velocity field and the forcing. It will come up in slightly different forms depending on the forcing. Just to give you an idea what comes ahead. So on top, I show 2D simulations of Navier-Stokes with the forcing that I'll specify later that comes from the active stresses. So just imagine this is a 2D turbulence. You see low amplitude of the forcing, medium and large, and you see the characteristic vortex dipole. I forgot to say this is always periodic boundary conditions in the square domain. Now below I do the same with random Gaussian forcing, and I could have just I could have just changed the labels, you wouldn't have seen any difference. So the question is not what forms, but how it forms, depending on the forcing. Okay. Before I actually discuss the transition, I'll take you very quickly through the derivation of a continuum model for dense active suspensions. And there are essentially two types of models. I'll mainly discuss one here, which is called a solvent model that has been devised by Jörn Dunkel and his PhD student Jonas Slonka. And what you have is you have the Navier-Stokes equations and you have an active stress here. And this is what you don't know. This is the collective effect of the bacteria, of the microswimmers on the flow. And the solvent model that they came up with was to postulate, and you can do part of this from first principles, part of this is ad hoc modeling, to say, okay, the effect that the microswimmers have on the flow is is resulting in an effective viscosity that is scale dependent. So you have your normal Newtonian viscosity, and then you have two additional terms that come from peculiar specific effects of the active stresses, and I'll come to that in a minute, how you can end up at this equation. What you see here, if you plot the viscosity as a function of wave number, then you see a negative part here, and this is what drives the system. So you have a local and scale linear instability that acts in a particular wave number band, and the boundaries are given, and the scale, the effective forcing scale is given by the two parameters gamma 2 and gamma 4. For completeness, there are different types of models that you can derive. The philosophy is a little bit different. This one I'll show how you can derive it from a two-equation model by essentially removing an equation for the bacterial flow. You can do the opposite and you get a pattern-forming system. The point that I'm making here has very similar small-scale structure. I'll be focusing on the solvent model here. Now you could ask directly, why do you model a system where you have a bacterial concentration and a solvent just by one equation? So in principle, you would say, well, no, you don't. You take two equations. You take one equation, which is for the solvent, so water, and you have the bacteria swimming in water. This is essentially what I've shown you before. So pi, well, here is the pressure. And then you have a different equation, which is, you can call it the bacterial polarization. So this is a vector field that is determined by, you can think of it as a coarse-grained effect of the bacteria. So this, in principle, it's called the bacterial polarization because if P doesn't vanish in mean, then you have a polar order in the system. And what I'll discuss very briefly is how to get from these two-equation model to a one-equation model, and then we continue with the transition. So the bacterial polarization is essentially advected by the flow. You have an effective pressure term. You assume in this case here that bacterial concentration is constant, which gives you essentially that P is solenoidal. And then you have various effects. So omega is the vorticity of the flow, omega cross P, and then you have here the strain rate. This is effectively what we would know as P dot gradient U, just written in a different way. And you have different parameters in front. That's why it's split, and you can derive this equation directly from first principles. The field H is related to the free energy of essentially, you can model it in the same way as an active pneumatic, and there are terms in it which give you the type of activity and the stiffness of your, in principle, of your active pneumatic. The stress tensor you can derive also as a gradient expansion from assuming that you have dipolar forces. And what you get is a term that we are very familiar with, and which effectively, if you derive a one equation model, gives you a renormalization of the Reynolds number, so of your nonlinear term. And then you have an additional term here, which will become very important. And this is the one that that is effectively in the end drives the flow. Okay, and alpha and beta are different so-called activity parameters that depend on the concentration of the bacteria, and it depends on beta also depends on the type of swimmer, so the direction of swimmer, so whether they're pulling or they're pushing, for instance. Okay. And so what I'm doing now is something relatively brutal. I say, well, okay, I have two equations. I actually want to get rid of one. So what I'm postulating is that my polarization field depends on the velocity in a linear way by through convolving it with effectively a filter kernel. And why am I doing that is because in a bacterial suspension, the hydrodynamic interactions are screened. So I can assume that I have a relatively sharply peaked function here. And I could come up with something more complicated, but this is a sort of first order approach. It's the simplest way I can try to go from the two equations to one equation. Now I'm making my life easier by, and this is also what I'm mainly interested in, is in the purely 2D case, where, as I said, both fields are solenoidal, the velocity field because I have incompressible flow, and the polarization because I have a constant bacterial suspension. So that means I can define a vorticity of the polarization field. So M is formally the vorticity, or the out-of-plane component of the vorticity, and omega is the normal out-of-plane component of out-of-plane vorticity we know in 2D. And then I assume, again, because hydrodynamic interactions are screened, that I can model G as a sharply peaked function. And if I do that, I can come up with a family of one-dimensional 2D PDEs, one equation models that describe these suspensions that depends on the choice of function that I'm taking. So for instance, if I take a Gaussian, or I can also take a sinc filter here. And then what you do, for instance, to derive this Linkmann-Dunkel model, you take a Gaussian filter, you Fourier transform it, you expand it in powers of what I would call a shape parameter, or of the width of the Gaussian. You Fourier transform back, so you get an expansion in powers of the Laplacian. So you expand essentially P in powers of delta U, and if you substitute that back into your equation for the stress, you have two components that matter. You have one which was pi pj delta ijp squared, which gives you essentially, that's what I said before, renormalization of the Reynolds number. Here you have an effective term here that you can scale out, and that shows up in an extra term, an extra factor here. And then you get an extra term which comes from the gradient of the polarization field, and that term gives you the effective viscosity. And it's exactly this form that you would get for the Linkmann-Dunkel model. Now, as I said, you can do different things. You can also take other filters, and if you take, for instance, a box filter in Fourier space or sinc in configuration space, you come up with what we call a piecewise constant effective viscosity. So effectively that tells you you have your normal viscosity, and then you have a negative part, which again is a local in scale linear instability, and you have viscosity at this, you have high viscosity at the small scales. And you can of course study a transition to condensate formation in both systems. We've opted for this one. We've also done an investigation in this one, because if you see how, if you change your parameters that give you the length of the forcing interval, you will very quickly realize that you cannot fix a forcing scale. So if you want to increase the intensity of your flow, what you get is you widen your interval, and you cannot just fix a given scale. It will always move, and it will always shift. Yeah. So this makes a very sort of clean comparison difficult. For this reason, we've opted for that model here. The other reason is slightly physical, in the sense that imagine you have a bacterium that swims in the flow. It has a characteristic swimming velocity. Yes?
Sorry, can I ask, is this actually relevant for a bacterium suspension where you expect a low Reynolds number? Or this
Yeah.
Because like you expect the U term to be small, or is this effectively
So yes. Okay. So I have a comparison to experiments in a later slide, but what you're saying is the Reynolds number actually big enough in a bacterial suspension for this to matter at all? So the Reynolds number in a bacterial suspension normally is, for the type of vortex that I've shown in the first slides, is 10 to the minus 2, roughly. You can estimate it. What you see with what we are doing when we see a transition is about 2 or 3 orders of magnitude higher. So in an actual experiment, I wouldn't see this type of transition. There are experiments that people do with magnetic spinners, and there you get Reynolds numbers of about 30, and there you start to see cascades. We don't see the transition that I'm talking about here, and the reason for that is because in all the derivations I assumed dipolar forces, and the magnetic spinners are vertical. So that would require a different, that's more close to a random forcing, I would say, rather than to something that preserves the phases of your flow. Does that answer your question? Okay. I can come back to the slides later on to make it. Yeah. Okay. So the other reason why, even though this is a very sharp transition here, is if you have if you would want to let's say you put more nutrients in the flow, so or more oxygen, your bacteria tend to swim a bit faster. You would expect with this type of model that results not only in faster speed, but also in a larger range of length scales, and that's not what you see in experiments. So in experiments, you see this characteristic size of vortex. So in that sense, there for practical reasons, this model is sort of a little bit more convenient. So with that, I come to what we've done in the numerical simulations. So we took a periodic domain on moderate number of grid points and moderate resolution. The reason for that is because we need extremely long integration times, and because we don't have large gas friction in this system. We fix the forcing band, and I only vary this amplification factor here. So there's a local and scale linear instability, and I will study the transition as a function of this driving here, of the amplification. And then just as 3 example cases, if I have very low driving, so this is scaled with the kinematic viscosity, then I have, this is the kinetic energy, then you have some disorder here. The kinetic energy raises if I drive the system more, which is not that surprising, and then suddenly I have, I sort of nearly double the driving, and I get to a very high energy state, and this is rescaled by a factor of 0.05. So this is enormous, and this is not surprising. This is what we observe or what we know from condensate formation. So this state here is essentially what you see is only the energy at the driving scale. Then we have slightly larger structures. And then if we have very strong driving, we see our familiar dipolar vortices. So I'm showing here only the energy, it's not the vorticity. And if you consider the corresponding spectra to those three states that I've just shown, so a weak driving, we have so the gray shaded area here in the energy spectrum are the driven scales. You have a scaling that is close to absolute equilibrium that you would get from predictions of statistical mechanics if there's no flux. And then we see that at intermediate scale, and then we have no flux to the small scales, to the large scales, I'm sorry. Then we have an intermediate case where we have slightly, we have some nonlinear interactions that transfer energy upscale, and at the very large scales we still have no flux. And then we have the most extreme case where we force very intensely, and we have the formation of a condensate, and you have the corresponding inverse energy flux. What's notable here is if you see that the energy at the forcing scale is actually smaller for the case where the condensate forms, and that will become that's very different if you force with a random forcing, and that is most likely to do with the direct coupling between the driven scales and the condensate through memory that the system has in terms of its phases. Okay. So if I now take as my observable the energy in the condensate, so I take the lowest Fourier mode that I have in the system, which is k equal 1, and I plot the energy against the driving. Then what I see is at a particular value I have a jump in that system, and the growth of the condensate with the driving is quadratic, and you can derive that by an energy balance. So that's expected, that it goes as nu squared. That comes directly from the equations of motion. And what we've done then, we traced a hysteresis loop, so we increased here, and we decreased the driving there, and you see that there's a small hysteresis loop. So there's some memory in this system. So you have and it's most likely connected with a direct coupling between the forcing scales and the condensate. Another way of discussing this is, and that comes back to the fact that you have a decrease in energy in the forcing scale. So if you consider the energy that you have just at the driven scales, so I'm plotting here the energy in the driven scales, and on the y-axis you have the total dissipation, or equivalently in steady state, because these are all steady state results, the total energy input. And the dashed lines here, you can think of that they rotate across your graph like this, with increasing the driving or increasing the amplification factor. So you have two branches. You have that below a critical point is this branch here, which I've called epsilon minus, so no condensate. So the black point here was the case where we had no flux to the large scales. And then we have a point which is very close to the transition, and then you have this jump where both the energy goes down in the forcing scales and the actual energy input. So it jumps down, and then it picks up again, and eventually it comes to the condensate states that are sitting up here. Okay. So this is a lot of characteristics of the system, and we asked ourselves then, okay, can we sort of understand this subcriticality? I mean, I was kind of alluding to non-local interactions, etc. And for instance, to persistent phase correlations, which have been seen in other systems. So, for instance, in the Favier et al., this was convection, where persistent phase correlation has been observed. And what we do here, it's also been done by Adrian and Alex differently, is to try if we can gain some at least descriptive understanding through a very broad low-dimensional modeling. So only to see if with a low-dimensional model, let's say 3 scales, can we obtain a similar phenomenology. And that is basically, well, this is based on assuming interactions that happen directly with the condensate that switch on after a certain threshold. So what we do, we define 3 sort of energy scales in the system, either the condensate or something that is between the forcing scales and the condensates, so K-min would be, formally speaking, and I've put these integrals here because I actually calculate the constants in my model from the DNS. So this, you can just think of an intermediate scale between the forcing and the large scales, and then we have the driven scale. So formally we also had a force scale. There is the small scales that is below at scales smaller than the forcing, and they only shift the transition. They don't have a qualitative effect. And then we model the interactions. So we have interactions between the driven scales and then scales that are sitting between the driven scales and the condensate. And we model that by saying that two modes at the driven scales feed into one in the intermediate scales. And we do a very similar approach here. Two modes on driven scales feed into one in the condensate. And why did we not do it the other way around? Is because if you have your triad interaction, you have two large wave numbers, and it's more likely that two large wave numbers have a small angle, and you give one small wave number to close the triad rather than having two small wave numbers connected to a large one. And here I've just put a Heaviside theta function, so a Heaviside function. So theta function here that tells me after a given threshold, I switch on these non-local interactions directly. So it would be nice to have a more sophisticated model. Here I've just put it in by hand, just to see if we get a similar phenomenology. And then we have a term that would resemble your cascade, and that is we have a process where the large scales, so between the forcing and the condensate, that feed into the condensate themselves. So you have two processes by which you feed the larger scales, either going from the input scales to the large scales and then to the condensate, or directly. And so we get a three-equation model with effective wave numbers and the coupling terms that I've discussed. And each of the coefficients in front of the coupling terms I can calculate from the DNS. And then I can go and I can, first of all, analyze it in steady state analytically and make a prediction, and then I can put it on the computer and it will run very quickly and it will give me some ideas. So first of all, if I solve it in steady state, I can solve it in two branches, either above, so either with condensate or without condensate, or with a condensate over a threshold. And I can come up with the following scalings in terms of the amplification factor. The main point is what you can say close to a critical point is that, or close when you're saying, you can say, okay, you have I have a nu plus and a nu minus in the two branches, and if you say, okay, they are approximately equal, what you can say, you get a prediction where, indeed, as we see in the DNS, that the energy, when I have a condensate, and the energy when I have a no condensate, that the input energy is actually lower, and that in steady state translates to actually lower input. So these are the predictions that I just get from having a very simple steady state analysis. And then if I run a number of instances of this model with different amplification rates, so I do the same as here, it's the plot that I had before. So all these data points that I've plotted here correspond to runs of the model with different amplification rates, and we get this jump here that we predict from the steady state. And we have effectively a similar phenomenology just from this simple model. Okay. So that tells us that even though the transition was put in by hand, at least a simple model like this can describe the broad features of what we see in the transition. So at least in this first order transition. Now I've spoken about non-universality in the title. I've not said anything about this so far. So what I come to now is the 2D turbulence setup that we're normally used to. So we have the 2D incompressible Navier-Stokes equations again on a periodic domain. Now I have a random forcing that is delta correlated in time, and I consider the effect of large-scale friction. So I fix the forcing band, I fix the viscosity, and now I vary only the amplitude of the forcing and the alpha, so the strength of the driving, the strength of the friction, the amount of friction. So these are results without friction, and they are very similar to what we would have in the active suspension case. So you have low driving, which corresponds to this state, which is essentially what you see just here is just the forcing. There's nothing else happening. Then you have an intermediate state where you have not some unsteady dynamics, and then you have the formation of a condensate. So this is very similar to what we had before, and you notice that we have extreme number of very long integration times. This is because with no friction, the condensate saturates in a viscous time scale. So this is why it's so slow. Then in terms of the spectra, there's also not really anything surprising. So for low driving, you see again that we have, at least at the large scales, we have absolute equilibrium scaling. What you notice here is that there's no non-monotonicity in the energy at the driving scale. So the more you drive, the more energy you have at the driving scale. And again, you have in the condensate state, you have the inverse flux. And when the condensate's lower, you have less inverse flux. So this is kind of the phenomenology that you would sort of expect. Okay, and so what I'm showing here is that in fact, if you have a random forcing as opposed to the forcing by the linear instability, that the transition is different. So it's no longer first order. So now you have a second order transition. If I vary the amplitude of the forcing, and I plot it against an amplitude, so the square root of the energy at the forcing scale, then what I get is at F over a critical threshold, I get essentially the normal form of a supercritical pitchfork. So I get a square root here, and then eventually, if I'm far off the bifurcation point, then this becomes linear, and you can predict that. By an energy balance. You say, okay, I have a strong condensate. So in the strong condensate, if I say my energy input, because I'm in steady state, must equal the mean dissipation. Now, if I'm in a very strong condensate, most of my dissipation will actually be happening in the condensate if it's saturating there. So that means I can relate the energy in the input to the energy in the condensate to the amount of energy that is, so the input rate. And because you have a Gaussian forcing, you can show that epsilon in is f squared, modular factor of 1/2. So that means that my amplitude here will, for a strong condensate, just scale linearly with the driving amplitude. So this is what you can get from there. And now coming to the effect of large-scale friction. So the dark red curve is without friction, and then I increase friction this way. And what you see is that you get different exponents. So I've only fitted very close to the transition point here. And what you see as well, that the actual transition point itself is not changing very much with friction. It's about 10%, maybe 5 to 10%, that the critical point shifts, but the exponent that friction has a clear effect on the exponent. And you see as well that the linear scaling here moves closer and closer to the critical point. And if I have strong friction, then actually it becomes directly linear. And that, again, you could expect. So by very much the same argument, so again, I take the mean input, which equals the mean dissipation, viscous dissipation, plus now the dissipation that I get through friction. And if the friction is strong, then I'll move, then I can make this approximation. This is very broad. I could probably have said here, okay, well, I have a condensate. It's mainly at k equals 1, so I should put here alpha plus 1, alpha plus nu, alpha plus 2 nu. The point is that again, I get a linear scaling, and the larger alpha is, the more I can move this towards the critical point. So this would explain why why I get a linear scaling here, as opposed to a square root that I get when I have no friction. And with that, I'll come to the end. So there's quite a lot of time for discussion. I've rushed probably a little bit. So the main message that I'd like to convey is that the transition to a condensate in 2D turbulence is non-universal. So if we take a model that is in a PDE model inspired by bacterial suspensions, by the dynamics of bacterial suspensions, where the active stresses result in a small local and scale linear instability at the small scales, we observe a first order, a discontinuous transition, as most likely because you allow for phase correlations to be maintained in the system. If I start to force the system randomly, I get a second order transition, and random forcing destroys all phase correlations that I have in this system. And the exponent depends on the friction. And I'd like to point out that a similar work has been done also by Grisha and co-workers. So in the Gross-Pitevsky equation, so for wave turbulence, there are different transitions to condensate formation. So you get a series of sharp symmetry breaking transitions as a function of the increasing wave action, and no symmetry breaking for random driving. So here you get, unfortunately, I forgot what is the exact state that you get, but you have different states. So isotropy is the first statistical symmetry that goes, and then then there are further ones. And then there's also an interesting discussion, I think, to be had about the different information content you have depending on the type of forcing. So if we consider the phase-space measure of this system, then that becomes time dependent. So this is work also done by Falkovich and Chavez, also people who are here, so it would be nice to discuss further maybe. So you have so your phase-space measure of the system becomes time dependent in turbulence, and then depending on which type of forcing you have different entropy extraction rates. So the extraction rate, I think that's been, so please correct me if I don't summarize your paper correctly, okay? So if you have random forcing, then the rate of extraction of differential entropy, so the difference between the entropy of your phase-space measure and the Lebesgue measure, that becomes, that is not explicitly dependent on the phase-space measure itself, but it does so when we have a local and scale linear instability. So there's clearly a different information content in the system depending on the type of traffic. It's probably not that surprising from a statistical physics point of view if you have a random system explores the phase space. So that's a discussion that I would like to have a little bit more in detail. And I have to admit, this hasn't been my thoughts. This was a referee kindly pointed this out, so you can speculate who that was. Okay. Okay, with that I take questions, and I can, for unasked question, I can leave the next slide up on the comparison with experiments. Thank you.
Alex?
So, close to the transition, so you are below the transition, there is no condensate, you slightly cross it. Do you form immediately a condensate, or is there some k to the minus 5/3, and then if you go even further, you form the condensate?
So this depends on the driving. Yeah. So here, I think here you can see quite nicely. So this is with random forcing. This is with random forcing. So so this state here is quite close to the transition. So it's above, so I have a small condensate here, but it's order 2 times 10 to the minus 2 or something on the scale. And I do see a scaling. It's a bit flatter than k to the minus 5/3, but that's also expected if I have a condensate, and this affects the scaling. So when I do the random forcing, then I don't jump immediately. I have a little bit, and then it starts to take off. And I have definitely a defined power law scaling in the middle.
Okay.
Yeah. If you go to the other case, where we have the first order transition. That's more extreme. I have a little bit, and it goes down, and then I have this huge condensate emerging, and there's
The blue is above or below the critical?
Blue is below.
It's below.
Blue is below, yes. Yeah. But very close. So blue is here.
Uh-huh.
Yeah. And you have to be very careful with domain size. So if you see the dotted lines here, we've done this with different domain sizes, and then rescaled the simulation to probe the effect of domain size. So if your domain size is too small, you'll probably expect, your jump will be much more pronounced than in larger domain sizes.
Okay.
I have a question, but I want to give priority to the room. All right, let me ask I was very interested in the model where you had piecewise constant mu.
Yes.
As a function. And I have two questions about this. I might have missed it, but what is the significance of nu equals 2 as the thing that y2? And then my second question was, because I'm not sure if I missed it, is there a correlation between the size of the condensate after it has formed and the position of the negative nu, or are these not necessarily related? Did the condensate grow to the size of the domain, or was it associated with the value of k's?
No, it grows to the size of the domain.
Yeah, regardless of where you have the negative diffusivity.
Yeah. No, it's like a standard inverse cascade, if you like. So it just goes to the size of the domain. Yeah.
And the nu equals 2?
And the nu equals 2, just that there's no particular significance. So it will also depend on, so for stabilization, we could in principle have another parameter, this one. And this will vary. So if you have a larger, this will vary the point of transition. Yeah. It's not going to change the nature, but it will vary the point. So this 2 has no significance.
Okay.
Yeah. It'll depend. So if I had put this larger, then it would have been 3 or 4. Yeah.
Okay.
So, yeah.
Take a 7-minute break.
Oh, I guess we do have a little bit of time.
Not enough? I'm just wondering if we're supposed to be on the clock or outside. All right, we have 7 minutes until the next talk. So for those of you who missed out on coffee earlier, including myself, we have 7 minutes, but please come back on time out of respect for our next speaker.